Hi boys and girls, this is lecture 6.5. The topic, exponential functions, differentiation and integration. And this will be part 1 of our discussion. Remember the natural log function, f of x equals ln x? Here's the graph. It turns out that the exponential function, f of x equals e to the x, is the inverse function of the natural log function. This means that ln of e to the x equals x, and e to the ln x equals x. Because these are inverse functions of each other, composing them results in x. Remember that e is not a variable. It's another irrational number like our friend pi. And here is the decimal approximation for e. Not that we're ever going to necessarily need all of these digits. We're going to use the fact that the exponential function and the natural logarithmic function are inverses of each other to solve equations. So we need to keep in mind that the natural log of e to the x is equal to x, and that e to the natural log of x is equal to x. In this first equation, notice that the variable is inconveniently located in the exponent position, so we'll need to undo this relationship by applying natural log to both sides. Natural log of 7 is about 1.946. But on the right side of the equation, since these are inverse functions of each other, the x plus 1 drops out of the exponent position. And now we're able to solve for x. This means that x will be approximately equal to 0.946. Now let's solve a logarithmic equation. Once again, the variable is inconveniently part of the argument of the natural log function. Well, to undo that relationship, we're going to need to exponentiate both sides of the equation. So e to the natural log cancels each other out, and we end up with 2x minus 3 equals e to the 5. E to the 5 is approximately 148.413, so we end up with 2x minus 3 equals 148.413. Let's add 3 to both sides. 2x is equal to 151.413, which means that x is equal to 75.707. Here, we review two properties of exponents as they apply to exponential functions. If you have a product of two terms with the same base, then you can add the exponents. If you have a quotient of two terms with the same base, you can subtract the exponents. We're also going to take a closer look at the exponential function and examine some of those properties. Since the exponential function and the natural logarithmic function are inverses of each other, we should not be surprised to see that the domain and range are interchanged. For the exponential function, the domain is from negative infinity to positive infinity, but the range is from 0 to positive infinity. The exponential function is continuous, increasing, and one-to-one on its entire domain. It is also concave up on its entire domain, but remember that the logarithmic function was concave down on its entire domain. And the limit of the exponential function as we approach negative infinity on the x-axis is 0, but as we approach positive infinity on the x-axis, the function becomes unbounded and approaches positive infinity. So what is the derivative of the exponential function? One of the most intriguing and useful characteristics of the natural exponential function is that it is its own derivative. Yes, that's what I said. It is its own derivative, which makes taking the derivative of exponential functions really fun. The derivative of e to the x is e to the x. The derivative of e to the u, where u is a function of x, will be e to the u, then times the derivative of u, du dx. So let's take these derivatives. We have the derivative of e to the 2x minus 1, and that answer is going to be e to the 2x minus 1 times the derivative of 2x minus 1, which is 2, and we'll rewrite that with 2 as the coefficient, 2e to the 2x minus 1. There you have it. What's the derivative of e to the negative 3 over x? Let's rewrite this as d dx of this function, e to the negative 3x to the negative 1. So we'll be able to use the power rule. Well, first of all, it's e to the negative 3x to the negative 1. Then times the derivative of negative 3x to the negative 1, which is 3x to the negative 2. So we can rewrite this answer as 3e to the negative 3 over x squared. In this last example, we're going to find the relative extrema of this exponential function. F of x equals x e to the x. To find extrema, we'll take the first derivative, set it equal to 0, in order to generate a list of critical numbers. So let's take this derivative. Of course, it is going to require the product rule. The first function, x, times the derivative of the second, which is e to the x, plus the second function, e to the x, times the derivative of the first function, which is 1, and there is our first derivative. Let's set it equal to 0 and factor out the e to the x. This gives me two factors to set equal to 0. Well, e to the x will never be 0. That can never happen because remember, this isn't a variable, it's a constant raised to a power, and thus will never be 0. But x plus 1 equals 0 gives us a critical number at negative 1. Now let's set up some intervals and see if negative 1 is a min or a max. I know we are looking at the graph and we can see what it is, but of course we should let our analysis support the graphical conclusion. So let's see what's happening to the left of negative 1 and to the right of negative 1. I'll let negative 2 be my test value in the first interval and 0 be my test interval in the second. I need to see what's happening in the first derivative. So let me look at f prime of negative 2. This gives me negative 2 times e to the negative 2 plus e to the negative 2, which is negative 2 over e squared plus 1 over e squared, which gives me negative 1 over e squared. Remember, this is a positive number and this is a negative number, so this is a negative value, which means the function is decreasing to the left of negative 1. Now let's find f prime of 0. That means the first term is 0 plus e to the 0 power, which is 1, a positive number. So that means the function is increasing to the right of negative 1. This confirms, of course, that negative 1 is a minimum value. Now let's find out what the y value is by finding f, the original function of negative 1. That's going to be negative 1 times e to the negative 1, which results in negative 1 over e. So the only extrema on this function is a minimum value at negative 1 comma negative 1 over e. That's it for today's lecture. God bless you, boys and girls.